Hi there and welcome to Chapter 3.2 from Stevens' Matrices, Vectors, and 3D Math. In this chapter we're going to take our vector valued functions that we saw in 3.1 and differentiate them. Right? It's easier than you might think. If you've differentiated single variable functions that look like this, we said alright, if you have a function f of x, you differentiate it, that's the derivative of f with respect to x right there, you get something that we called f prime of x, right? And so it is assumed here in this textbook that you took Calculus 1, and so you are familiar with this process. For example, if f of x was equal to 3x cubed plus 7x squared plus 5, then f prime of x was 9x squared plus 14x plus 0, right? Okay, so, but now we're going to be talking about the derivative of a vector valued function. Get the mic a little closer here. And remember, a vector valued function had, if our original function was r of t equals x of t, y of t, and we'll assume we're in 3 space, so we have a z of t. Right? So we have a vector valued function. The derivative is just r primed, and we take the derivative of each term in there. Right? Really easy to do. So if you can take the derivative of a single variable function, or a function of one variable, or I guess more accurately, a single function of a variable, then you can take the derivative of multiple functions of a variable. You just take the derivative 3 different times, right? And so that's what that's sort of the informal definition. In fact, I'll give that down here. We'll do that one first. Informally, if I have a vector valued function that looks like this, then its derivative is found by just taking the derivative of each of the individual functions inside the vector valued function. More formally, it is actually defined exactly how the derivative of a single variable is found, right? If I had a function f of x, then f prime of x would be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. That's the old formula. Definition of a derivative you may or may not remember from calculus. It is the same as we have for a vector valued function. But all that means is that you go in and you apply this process to each function, x of t, y of t, and z of t, and you just end up with the derivative of each function residing in the appropriate location of the derivative of the vector valued function. And the notation is the same. You get the little prime notation. And you could also write this as the derivative of r, the vector function, with respect to t, if you wanted to. But generally we use this notation. And something you've probably saw in calculus, and we will continue, is the position, velocity, and speed, and acceleration. Right, so position, we'll generally consider that our original function. That is r of t. That's our original vector valued function. It gives us the location, in 3 space, if that's x, y, and z. This position vector valued function will give us some point in 3 space, or 2 space. Right? But it will move, that position will move as t increases. Right? That vector will move around. And as it moves around, that will create a velocity vector valued function, which is just the derivative term by term of the position function. But now this velocity vector valued function, it will have, suppose it's right down here and I have that. Suppose that's v at some point or another. It will have a direction and a magnitude, right? And if I look at just the magnitude, then I'm talking about speed. So speed is the magnitude of my velocity function. It's how big that vector is, right? How long it is. And then finally, velocity is so we have velocity is the derivative of the position, and acceleration is the change in velocity, right? You press the accelerator, that changes your velocity. So acceleration is the derivative of velocity, but since that was the derivative of position, acceleration is just the second derivative of the position, which is just term by term differentiation twice on my original position function. Right? And these have geometric interpretations that we'll get into right now. So the first thing I'm going to talk about is an example in 2D, this position function. Right? And what that looks like is an ellipse with x radius 4, y radius 2. So you go 1, 2, 3, 4, 1, 2. And as t goes from 0 to 2 pi, this ellipse gets sketched out like this. Right? Negative 1, negative 2, negative 3, negative 4, negative 1, negative 2. All right? So that's x, y. And it gets sketched out in this direction. Right? As t goes from 0 to 2 pi. Now, if I want to find the velocity and the acceleration vectors, or vector valued functions, easy enough to do. I just take the derivative of 4 cosine t, which is going to be negative cosine. So cosine goes to negative sine. The 4 comes along as a constant, and I get the derivative right there. And I take the derivative of my y valued function. Derivative of 2 sine t is 2 cosine t. So that gives me my velocity right there. And if I differentiate one more time, sine goes back to cosine. I still keep the negative 4. That's another derivative there. If I take 2 cos t, now going from cos to sine gives me a negative. And I get negative 2 sine t. Right? Okay, so what good does that do us? What does that mean geometrically? So here's what I want to do so you can sort of see how this works geometrically. Suppose I pick a time t equals pi over 3. Right? If I think about t equaling pi over 3, my position of pi over 3 is, let's see, 4 cos pi over 3, 2 sine pi over 3, right? And pi over 3, that's this one up here. So let's see, that's 4 times 1/2, so that's 8. And this is 2 sine of pi over 3 is the square root of 3 over 2. So it's 8 root 3. 8 root 3. Right? And to point out where that is, that's this point here. I can't get the whole book on my page here. Oh, maybe if I make it bigger. 1 second. Here we go. Still trouble squeezing it on. So I'm going to go back to my little drawing up there. So I'm right here. That's at the point r of pi over 3. So this point right there is the position vector at pi over 3. Right? Having trouble with my pen up there in the top corner. Okay, in other words, if you scroll down onto your page, it's this position. So there's my position vector at the t equals pi over 3. Right? T equals pi over 3. That's a little clearer. That's a nicer graph. Okay, so what I want to do is I want to find the velocity vector and the speed at that time. Now the velocity vector at that time is just a matter of taking this velocity vector valued function here and sticking in pi over 3. And when you do that, you get this result, and simplify, you get negative 2 root 3 and 1. And the speed at that particular time is just the magnitude of this vector. So I take this, square it, add them together, and take the square root. And so the speed is square root of 13. And so the trick is to sketch the graph so that all this sort of ties in together, right? I'm going to sketch r of t for the whole period, which I just did up in that graph up there. And that's what this graph is down here. That's I do my whole sketch, 0 to 2 pi. It actually starts here, goes this way. All right. That gives me my ellipse, as indicated by the blue line here, the blue curve. And then r of pi over 3 is what I did up there as well. So there's this is the actual vector, right? The position vector, and it ends at this point that we determined was 8 root 3, right? Right. And so then whenever I did the velocity, v of pi over 3, that was this right here. Right? So v of pi over 3 equals negative 2 root 3 comma 1. And if I sketch that down here, that's going to be negative 2 root 3. Now that's just a little bigger than 1. So I'm actually pretty far, I'm pretty close to 4. Right? It's this right here, negative 2 root 3 up 1. So I'm at this point right here. Right? But that isn't really where the velocity vector is originating. The original velocity vector, this v of pi over 3, is originating at the terminal point of my position vector. So there's sort of what the velocity vector looks like. It tells me that at exactly this point in my travels around this ellipse, as I go around, as soon as I hit this point, I am going in this direction, right, with this much speed. Whatever the length of that is the speed. Right, so the arrow, the vector direction tells me where I'm going, and the length of that vector tells me how fast I'm going. Right, so it does, hopefully that makes it a little more geometrically, it should make sense, right? Whenever you draw a velocity vector at some terminal point, it should be tangent to the curve that's being sketched out in 2D, or 3D for that matter. So for example, if I go to 3D, suppose I have this is a sideways helix. It's very similar to the vertical helix we had in chapter 3.1. And if you think about it, this is just my x variable is increasing linearly with t. So x is just increasing that way as t goes from 0 to 4 pi. And this right here is essentially an ellipse with y radius 3 and z radius 4. Right? So I have 3 this way, 4 that way. And I'm sketching out circles, or these ellipses, and as t, so I start here, as t increases, I'm moving further down the x-axis. Right? I got kind of busy right there. Okay. And so because I'm going around, t is going from 0 to 4 pi, but I have this multiple of 2, so this would be 2 periods. But since I have 2's out in front, I'm actually getting 4 periods. That's why you're getting 1, 2, 3, 4 rotations around here. Alright, and I give this point in problem a little further down here. This is the point 1, 0, 4. Let me just locate that right here. This is the point 1, 0, 4. It is on the top of this first, after you go around one time, it's at the very top there. Okay, so the trick is, I want to find the velocity. My goal, I'm really trying to find out, is what is this velocity at this point on the curve? What is my velocity? Right? But I've asked a few questions along the way, and you can get this function or the file that made this graph from the Chapter 3 repository. Okay, so let's find the derivative, giving us a velocity. So it's not that hard. Let's see, we're up here. I'd like to get both these on the same page, but it doesn't look like it's going to happen. A little bit. So there's x, and x is just, we'll call it t times 1/4, right? And when I differentiate that, the t goes away, and I'm just left with 1/4. So there's my x value for my x component of the velocity vector, x. Now let's take a look at the y component. If I differentiate this, I'm going to get 3 cosine 2t, but the chain rule is going to bring in that 2. I'm going to pull that out, and I'm going to get 6 cosine 2t. So that gives me my y component of the velocity vector. Likewise here, I'm going to wind up with negative sine 2t, but by the chain rule, that 2, I'm going to get a multiple of 2 out there, so I'm going to get negative 8 sine 2t. So that's my z. Right? And then the acceleration is simply differentiating these. So when I differentiate a constant, I get 0. When I differentiate 6 cos 2t, I'm going to get negative 6 sine 2t, but the chain rule is going to give me another 2, so I get negative 12 sine 2t. And then whenever I differentiate negative 8 times sine 2t, I get negative 16 cosine 2t. So I have my velocity vector my velocity vector valued function, and my acceleration vector valued function. And here I want to find the velocity at this point. So part 2 says, what is the velocity at this point? Now, the trick here is that you know the point where you want the velocity. It's at the point 104. It's that point. You can see it, right? But in order to find the velocity, if you look at velocity, it is a function of t, right? I need t, right? We really need t, not the position. But that's pretty easy, because if I take a look at this, I'll go back to my very original position function, right? And I know that this is 1, this is 0, this is 4. Right? And so you can set any of these equal to their associated components and solve for t. For example, if I have t over pi equals 1, then t equals pi. So notice, if t equals pi, and I plug that in here, x is 1, 2t is 2 pi, sine of 2 pi is 0, and then cosine of 2 pi is 1, so 4. So this is what I have. T is pi. That's the thing I need. If I want the velocity at this particular point right here, I need to figure out what value of t gets us there. And we figure that out. T equals pi. Alright, so now all I have to do is take t equals pi, stick it into my velocity function, and I get 1 over pi, that's constant, 6 cos 2 pi, negative 8 sine 2 pi. You plug those in, cos 2 pi is just 1, so I get a 6 here, and sine 2 pi is 0. So there is my velocity vector valued function at the appropriate time. Now if you were to put this in at the origin, right, the origin here is a little strange. The origin is like right down here somewhere. And I need to put in the velocity vector, which is 1 over pi 6, 0. 1 over pi 6, 0. So if I was to sketch this down here, I'd go in the x direction 1 over pi, which is like 1/3, and then 6 in the y direction, and 0. I wouldn't go up at all. So basically, I would be going from here to here. That's what that velocity. And specifically, if you locate it back then at the original point, it looks like this. So this tells us the direction we're tracing out this curve. It tells us what's happening. It says we're going in this direction, which is what the clockwise direction if you're looking that way. And specifically, at the very top of this helix, there is no z component, so this arrow is actually flat, right? It's flat across the top of that helix, right? And most of the velocity is heading in the y direction. But it is moving out in the x direction a wee little bit as well. So it sort of gives us a little bit more information about our motion along some curve in 2 or 3D. Right? And then again, you might say, I really like the old y equals f of x. I hate to see that go away. The fact is, it is sort of going away. But if you still have y equals a function of x, and then you'd say, oh, y primed equals f primed of x. We can do this stuff with vector valued functions, right? And if you recall from the last chapter, we said, all right, if we want to recreate y equals f of x, we just create the vector valued function r of t. This is x, this is y, right? So I can create that, and then to get the derivative, right, you're just going to differentiate the position vector valued function, right? So let's start off with an example. Suppose we start off with y equals x squared. Y equals x squared. And if you graph that, looks like this, right? Parabola. It's a terrible parabola. And my pen's a little... My pen writes so smoothly that I have trouble. I get no grit like I do on with a pencil. Okay, so, and I want to find out what is the slope of the tangent line to the curve y equals x squared at the point 3, 9. Suppose this is 1, 2, 3, and this is the point 9. So this is the point 3, 9. All right, and I know I'm going to get a slope that looks like that. All right. All right, so if this is one-dimensional calculus, we'll just say, all right, f of x is x squared. The derivative is 2x. We plug in x equals 3, and we get a slope of 6. So it means that this tangent line here has a slope equal to 6, right? So that's standard calculus 1 of a single function of a single variable, right? Slope equals 6. How do we regain that in terms of a vector-valued function? Well, the first thing we'll do is recreate that function in terms of a vector-valued function, right? So there's x, there's y, right? And notice in this case, y equals x squared, just like it did up here, right? Okay, so now I take the derivative, and that's just going to be, I take the derivative of t, I get 1. The derivative of t squared is 2t. And when I plug in t equals 3, that's the same thing as plugging in x equals 3. I get v of 3 equals 1, 6. So if you were to put that in the xy plane, xy, that would be 1, and then 1, 2, 3, 4, 5, 6. It would be this vector, right? 1, 6. And the slope of that vector is just rise over run, or 6 over 1, 6. There's that derivative. Right? That's the slope. And so to summarize this into what's pretty straightforward, a pretty straightforward rule, suppose you like y equals f of x. You can create that as a vector-valued function, r of t, where x gets the t value, right? It's just t, and y gets f of t. Instead of the x, you stick a t in, right? And then if you want the slope, in standard single function form, slope is just called f prime of x. But in vector valued function terms, we call it v of t, or the derivative of r of t. The t differentiates to 1, and the f of t goes to f prime of t, right? And your slope is really sitting right there. And you just stick in your value of x. Make it t, stick it in there, and that is your slope. Right, so we've lost nothing by moving into vector-valued functions, and we have gained so much. You know, now we can move around in 2 and 3 space. As time increases, we'll trace out some curve, and at some point on that curve, we can get the velocity, the acceleration maybe, and the speed. Right, so it tells us a lot about motion in 2 and 3D. And I believe that wraps us up from this chapter. And I will see you in chapter 3.3. All right, bye.